Hello, so in this tutorial we are going to implement an A-star algorithm for pathfinding, so we can build towers and it would generate the route for the enemies. So I have this script that just shows here how we calculate, from which node we calculate the path. Of course you can use it in any way, you just need to pick two nodes on the map and you can calculate the distance between them. Now I can calculate the path between anything on the map. Right, so given this map, we want to calculate the path between this portal and this portal, and we simply need to get the neighbors of the starting area. So this starting node, we get those three nodes over here. Only this one is walkable, so we look at this one and calculate its cost. The cost would be how far away we moved from the portal and the distance to this portal. So let's say it's going to be 6, 6 for the x distance in here, so 5 for the x distance and 1 for the move. Now this one has this node and this node as neighbors, and while those two being unwalkable, so the cost for this one going to be 8 and this going to be 8 either. So again we got distance 1 of y, so we're actually getting further away from the end than the start, right? And the top one is the same. Now if we look at the bottom one, it has only one neighbor, so it's going to be this one and its cost is 10. Again, we're getting further away. And then we look at the top one because it has the lowest cost for the available nodes, so available nodes would be those two, right? And the cost for his neighbors is 10 and 8 over here. So because we're getting closer to the end and further away from the start, it's actually getting the same score. Then if we look again, we get those nodes with a score of 8, and actually those bottom ones actually do have the score of 8 either. So now we can see that this route or even this route is actually the best routes, and it would pick any one of those based on how the algorithm works actually. So yeah, let's look at the pseudocode now. So we would create a function, it would get a start and end position. This function would return us a list of all the nodes we have in the way. We have an open set. This one will be a set containing all the nodes we didn't look at yet. The closed set would be the opposite, nodes we already looked at, so we do not want to look at them again. First of all, we add the starting position to our open set, and as long as the open set has at least one member, at least one node, we will look at the first node inside the open. So the first node would be always the lowest cost. We will do this later. Now, if the current node would be the end node, we finished, and we would just get the path. Now, if it's not, then we remove the current node from open and add it to the closed set. Then we will get all the neighbors in the current node. And for each node inside the neighbors, we would just watch if it's walkable and not in the closed set. We will then see if it's not in the open set. If it's not in the open set, that means we are seeing this node in the first time, so we will make sure it's reset. So basically we would set the node cost to be the maximum value possible, and that's it for this line. And in all the other cases, we would simply update the cost. So if the cost was lowered, we would add this node inside our open set in a new position. Of course, if a reset was made, so this would 100% would return true, and we would add the node inside the open set. And in all of the cases, if never current was equal to end, we just return a null. That means there is no possible route to our end position. So let's create a new pathfinding script, and we would add public list of all the nodes and find path. This would get a node start and node end. And first of all, we need to create an open set. So list of node open, and this would be new list. And now we also need a hash set for the end. So the reason it's a hash set is because we do not care about sorting, and we only want to have one copy of each member inside the close set. So now open would get the starting node. So get start, and while open dot count is greater than 0, we simply want to check if open. So we get the first, so var current is going to be open at 0, and if current is equal to end, we return a null for now. So found a path. So we need to return a path. So basically, let's create this other function. So list node traverse path, and this one going to get node end and node start. So the path would be in reverse, but whatever. For now, return null, and let's just put it inside of here. So the current would be the end, and now if this is not the case, we simply say open.remove current close.add current, and now we loop over all the nodes that are neighbors. So var node in current.get neighbors. So get neighbors, but there is no such function. So let's create this one. So let's look at the pseudocode for neighbors. On the paper, it's really simple. We only want to get the top and bottom, right and left nodes. So we would do this by creating a list, and then we would loop with I between -1 and 1. And if I is equal to 0, you can see that node at x plus 0, this would be exactly the node here. And if this node exists, so what we need to do is just create a method for node at that would return a null if the node doesn't exist. So if we, for instance, trying to get the node between in -1 and 0, so there is no such index -1, and this is it. So neighbors is pretty simple. So let's create the node at inside the board and the neighbors inside each node. So inside the board, let's create a public node get node and int x, int y, and now we simply say if x is less than 0 or x is greater than size x -1, or x or y less than 0 or y greater than size y -1. So if it's greater than size y y minus 1, it's also size, exactly size y, and it's out of the area. Now return map x, y. So in this case, it's inside the bounds. So we want to add the neighbors function. So this would return a list of neighbors. So get neighbors. And for this one, again, we just want to create a loop. So I equal to -1, I less than 2, I plus plus, and if so var node is going to be equal to get. So board.get node at x plus I y. First of all, if I is equal to 0, oops, we just say continue. And if node is not equal to null, we want to add it inside the list. So list node n. So let's call it just list. We simply say list.add node. The same thing for the y. And plus I. Okay, and return the list. So the first thing we check is if the node is walkable or not in the closed set. So how would we define walkable? Well, we can do it by two ways. Either we can say that the node object over here would have a walkable or unwalkable settings, and then inside the node we would just create a function over here that would say public bool walkable and get return node object dot walkable, right? So of course, if node object is not equal to null, and either way we just return true. So no node object, so it's true. But in my case, for now I don't really care, so I would just return type is equal to 0. So if there is node object, it would be unwalkable. But if you want to have node objects like towers that you can pass through them, and for some reason, this would be the way to go. So we're back inside the pathfinding. Now we say if node is walkable and not inside the closed set. So if closed doesn't contain node, and we want to update the node values, so update cost, right? So we don't have this, and if not inside node dot open dot contains node, we want to actually say node dot reset cost, right? Same, we don't really have these functions, so let's create them. So the cast function would be the distance in x's plus the distance in y's plus the number of moves it took to get to this point. And if we look at this diagram over here, let's say this would be the start position and this is the end, and we look at this node over here, and let's say before that we had this cost calculated, so the number of moves to get to this point was like 3 or something, and the distance in x would be 6 and the distance in y would be 0. So the cost of this node would be 9, right? And now we calculate this cost. So the cost for this node is, so the number of moves to get to this node was 1, so we dropped to 7 over here, so the new cost would be 7. And we know that now the fastest route is like this instead of going something like this. So if the new cost is greater than the old, is less than the old cost, we just need to update it. We would save the number of moves would be, if this was 1, so the number of moves to get to this node would be 2, right? And we just save the current, so the node before that, to be a pivot, so we can trace back from where we came. So back inside the node class, we want to add public bool, update cost, and this function wants to get the node end and the node current, right? So if so now we need a cost in here, so private, or actually public float cost, and actually this would be int, and public node, let's call it pivot, so this would be the current node. We would just save it, right? So let's say var n cost, so this would be the new cost, would be the distance between the x's plus the distance between the y's. So math abc, distance in one dimension is simply just the absolute value, so math f abc and dot y minus y plus current dot moves, right? So we also want to have public int moves is going to be 0, and if the cost is greater than n cost, it means we want to update it. We found the shorter path. This also means that moves so before that the pivot was some other node, right? So that means that the moves would have been some different value. So current.moves plus 1, and pivot would be current, and we would return true. And if this didn't happen, we return false. Now we want the reset function, so public void reset cost, and this would simply nullify all of those. So moves is equal to 0, cost is equal to int max value, int max value. So we want this to happen 100% of the time, and pivot would be null. Oh, so this is me from the future, and I want to address one thing. Maybe you want to make nodes that are slow to work, or you want the algorithm to try to avoid. Now, the way you can do this is you simply say this node over here, let's say the node in the middle would have an extra cost of 10. So let's say you have here a node dot like penalty of 10, for instance, and you just add it inside the cost, so node dot penalty. Now this would always be inside, and that would mean that after that, when we sort for the fastest route, other nodes with penalty of 0 would most likely be picked over this one, and you would simply skip this node. But if there was no other path rather than this one, you would simply go over to this node. So making a slow moving tile or stuff like this is pretty damn easy. First of all, let's say that this is going to be static. There is no need for this to be a method of pathfinding. And now if we updated the cost, right? And we need to pass start and current. We want to resort the open list and edit inside the right place. So if first of all, if nothing happens, we return null. So if there was no path, and we want to create a function to actually update the open list. So public static void insert node. So we pass the list of nodes open and the node. Okay, so how would we make sure that the list here, so the open list at position 0 have the lowest cost node? So let's assume we have the array, something like this, right? So this is the cost for each node inside the open list, and we try to add a new node with a cost of 6, right? So what we're going to do is we're going to loop over the members of the list over here. So in the first run, when I is equal to 0, we look at 3. So 3 is less than 6. So we just go over it and we look at 5. So again, 5 is less than 6. We look over it. And when we get to 10, 6 is less than 10. So we break. And because we break, we insert 6 in position 3. So position 3 would be here, and you see we have a sorted list. And of course, if this would be 1, we would insert it in the 0 index. And if it would be something like 16, we would go over all the loop over here, and we would add 16 in the index of 5. So this list size would be 4, right? But I would get to 5 in the end, so we would add this here. And this is why it's always sorted. By the way, this is called insertion algorithm. So back inside the pathfinding, we say if node, if open dot contains the node, we want to remove it. So open dot remove node. So to make sure that we would not have duplicate of the node at different positions. And now we want to say for I, and length is going to be open.count, and if node.cost is less than open.I.cost, that means we need to break. And if we broke, we simply say open.add insert and node, so at I node, right? But I doesn't exist, so let's say I equals 0 here, and this now would work. So now we would always have a sorted list. So we say insert node, so open and node. And with that, I think we finished. Right, so now we need to actually get the path. So when we found a node that is exactly the end position, let's say it's here, we can remember it has a pivot, right? So we get from the end node and look at the pivot of the end one, and we get some x over here. Then let's say we get this node, and then this node, and maybe this node. So basically, as long as our node, our pivot has another pivot, we continue to loop, and we would stop either when the pivot is null or when the pivot is actually the starting position. So let's implement this. So okay, so we go inside the traverse path and we create a list, a node, let's call it path, right? And we say var node, this would be the end, so var current, this would be the end, and path.add current, and if, so while current.pivot is equal to, is not equal to null, and current is not equal to start, we would simply say a current is equal to current.pivot, and then we say path.add current and return path. So we got the pivot of the current node. So we go from the end, we look at its pivot. If it's not null, we add it to the path, right? And again, we do the same thing, and we stop if current is the start or the pivot, the next one is actually null. Just to be on the safe side, let's make some way of this stopping so it won't fail. So int max runs is going to be start.board.size x times start.board.size y, right? So there is no way we would go for over these times of nodes because there is exactly that many. So if c is less than max runs, and in the end let's just say c++ and start dot reset cast, because we can remember start actually never was reset, and just to be on the safe side, so start dot moves would be actually 0 and not some random value. So I've made this very inefficient method that would just get the path between the x start, the y start, and x and y end and nodes. Simply, if recalculate is true, then we and the board map exists, we would recolor the nodes, whatever. So you can see it highlights the node between two nodes. It's very inefficient. Do not use it. Now we can see it's working, and we can calculate the path. We can move the points we want to calculate, right? And it would always give you the fastest route possible. And now let's see how well it would work for a huge map. So let's say 51 by 51, and let's calculate for 2 ends, right? So 15 should be fine. And now we can build towers, and it would get you the fastest route. And let's build something like this, right? So you can see it works pretty great, and it only takes about 3 milliseconds to get the route, and consider it's a tower defense, you don't really calculate the path that very much. I would just use the pathfinding each time I create new tower, and that's it.